I was asked to make a video about sine and inverse sine. Well, really about inverse sine, but that means we're talking about based on sine. I'm going to graph sine of x first because an inverse function is going to have the same xy ordered pairs as its inverse, just with the x's and y's reversed. Maybe that's an important point. So sine is the inverse of inverse sine, and inverse sine is the inverse of regular sine. Right? You can't have one inverses are inverses of each other. So sine has the ordered pair 0, 0, pi halves 1, pi 0, 3 pi halves negative 1, 2 pi 0, negative pi halves negative 1, negative pi 0. Lots of other ordered pairs, but that'll do it for what we need today. Now, I'm going to grab some points here for inverse sine, but hopefully you'll understand why not all of these points are going to be used. So 0, 0 becomes 0, 0 on inverse sine. Pi halves 1 becomes 1 pi halves. Pi 0 becomes 0 pi. So hopefully you can see. This is what kind of this part of the curve of sine is going to be created on the graph of inverse sine. And then the graph is going to kind of keep going up here. So let's see, negative pi halves negative 1 becomes negative 1 negative pi halves, and negative pi 0 is 0 negative pi. So I suppose the important thing to note is inverse sine is supposed to be a function. And when you look at this graph, let's say at x equals 1/2, inverse sine has multiple outputs. Or this graph has multiple outputs. And you can see even if you continued up here, well, we know sine oscillates forever, right? Infinitely many periods. So I guess that means what we have here is not a function. So this graph actually doesn't represent inverse sine of x yet. So maybe we can figure out how we can change that. So really we want so from negative 1 to 1, that's all of the outputs of regular sine from negative 1 to 1. We want to preserve that from negative 1 to 1. So that means I'm probably going to be keeping this part from 0, 0 to 1 pi halves on inverse sine. That's up here on regular sine. Once we get to pi halves or 1 pi halves, this graph kind of doubles back on itself, at which point our graph is no longer a function. So we want to get rid of that part of the graph. So I'll just erase it. And so that means over here we're doing what's called restricting the domain. So what would the last place that sine of x be defined when we're changing into inverse sine? Well, we're doing an artificially restricted domain of something up to and including pi halves, okay? Which means the range down here for the graph of inverse sine would have its maximum range also including pi halves, since the domain of a function is the range of the inverse of that function. So we're going to trace back on inverse sine's graph until we see a similar kind of repetition of y values. Our graph no longer is considered a function back here. So we want to stop our graph at negative 1 negative pi halves, which means we're keeping this part of sine, and I guess the restricted domain starts at negative pi halves. So really, we're only keeping, I'm not going to erase the whole thing, we're only keeping this little part of sine of x in order to make the inverse of that part also a function. Now, I'm talking like we, but this is not me and you deciding. This is everybody's already deciding. I'm just trying to give you the ideas. So let's look here. So the range of sine, the part that we're keeping, is from negative 1 to 1 inclusive. That's good. That means we have all possible outputs of sine. That's all we can get from negative 1 to 1. And that negative 1 to 1 is also the domain of the inverse sine function. Okay? And so that should sort of make sense. If we're doing the inverse of sine, that inverse sine takes ratios. We should only be putting ratios into inverse sine from -1 to 1 that could come out of regular sine from -1 to 1. Okay? And so now we're going to do a couple of simplifications to hopefully make sure you sort of get this, because just like the square root of x and x squared, sine and inverse sine aren't perfect inverses. So let's think about this. Down here, I have inverse sine of 1/2, and you may have memorized this, but 1/2 is right here. Inverse sine of 1/2 happens to be pi over 6. Now, don't confuse that with give me any angle give me any angle that if I took sine of it, I would get 1/2. It's much more specific than that. Look at this graph. So when x is 1/2, when the angle is the ratio of sides is 1/2, how many places are defined on this curve? Actually, just one. This is an inverse sine function. If we had graphed all of the other parts of sine, then we would have had lots of places where this graph was equal to 1/2, but then not a function. So what's inverse sine of 1/2? Pi over 6. What else? Nothing. Anyways, so we take sine of pi over 6 and we get 1/2. So in this case, sine of inverse sine of 1/2, when we do sine and the inverse sine, we get to back where we started, 1/2. So I'm talking about the same spot over here, inverse sine of pi over 6. So let's look at the graph of sine. Pi over 6 is somewhere about here, pi over 6. So we should know by now sine of pi over 6 is 1/2. Also a function, right? Sine is not equal to 1/2 anywhere else. Or sine of pi over 6 is not equal to anything other than 1/2. So sine of pi over 6 is 1/2. And inverse sine of 1/2 is pi over 6. So this is pretty cool. I guess in this case we also have a kind of perfect inverse sort of thing where we take inverse sine of an angle and get back to that same angle. Let's see if this happens always. So inverse sine of 1, well, go up from 1 and we get to the angle pi halves. And so again, we're not saying give us any angle where sine is 1. We're saying the specific one on this graph. So let's see. Sine of pi halves, we know that. Sine of pi halves is 1. So again, a perfect inverse-y sort of case. I'm actually going to continue down on this left-hand side. So let's see. Inverse sine of negative root 2 over 2. What the heck is that? Well, we kind of have figured out root 2 over 2 corresponds with things that involve pi fourths. Negative root 2 over 2 is a little bit smaller than negative 1/2, so we can figure out that's probably negative pi fourths, which it is. So we have sine of negative pi fourths. Well, what's sine of negative pi fourths? I don't have it on this graph, but let's see. Sine of negative pi fourths is, well, that's also going to be that negative square root of 2 over 2 thing. Okay? And so it sort of appears we're always going to get the same ratio back that we put in, but that's not the case. We actually only get the same ratio back when our beginning ratio is put into inverse sine first. Right? So it's not like I could put some number that's outside of here. So when inverse sine is on the inside, sine of inverse sine of x is actually always going to be x. That's pretty nice. Basically, because we're talking about this restricted part of the curve that we're keeping on sine. You're going to see in my other examples that when we have ordered pairs or places on the graph of sine that are not on this restricted part that we keep on sine to get to inverse sine, we don't necessarily get back to where we started. So the first time we did, inverse sine of pi over 6 ended up being sine of pi over 6. But let's look at sine of 2 pi thirds. Well, you've probably memorized sine of 2 pi thirds. Sine of 2 pi thirds is, let's see, square root of 3 over 2. Let's see if that's right. So 2 pi thirds is somewhere up here. That's actually off our restricted domain part. And so now we're thinking, well, what's inverse sine of root 3 over 2? Oh, I said pi thirds. Oh, I did say 2 pi thirds. Okay. What's inverse sine of square root of 3 over 2? Well, let's see. Square root of 3 over 2 is somewhere in here, which means we're talking about pi thirds, not 2 pi thirds. We're talking about pi thirds. So we actually get pi thirds out. So I guess it's not true that inverse sine of something is always, I don't know, whatever's inside. I don't know what I was thinking when I wrote negative root 3 over 2. Maybe we should write a common angle inside of sine. So let's think like negative pi fourths. Sine of negative pi fourths, well, let's see, negative pi fourths would be here. Sine of negative pi fourths is negative root 2 over 2. And inverse sine of negative root 2 over 2 is negative pi fourths. Okay. And so I'll skip to it. You can ask for more examples later if this isn't enough. But inverse sine of x is x, but only if x is less than pi halves and greater than negative pi halves. Let me know if you need any more on inverse sine of x.